blaze through this. We already talked about linear phased array transducers, right?
Yeah.
Linear phased array transducers. What kind of, I already kind of have it up here. What kind of image shape is this, guys?
Fan. Sector.
Image shape, sector shape, right? Sector shape, okay? So even though it's a linear transducer, what makes it, is how the beam radiates out from the probe itself, okay? So I want this right here is talking about transmit focusing. I was on here thinking about Dewey, and I was messing with my PowerPoint, and I want to just show you guys how transmit focusing works. So I have, what is it called, messing with the lines. So I'm just going to show you how it goes down the same scan line. It's not that accurate, but it's pretty accurate, okay? So I'm going to blaze through real quick. So it'll send out, because remember I did it in the wrong color the other day, right? Y'all remember that? So it'll send out, boom, that first line like that. That first line will come back. Then it'll send out another scan line down that same one, that same scan line, and go back. Then it'll scan out another scan line at the deepest depth, then that same line, scan line, and go back. Only thing is, it's only going to take information from the appropriate areas, okay? So that scan line is not going to take any information from deeper depths. It's only going to take any information from the shallow, intermediate, or distal depth, depending on how many focal zones you have up, right? Because if I only have 2, then it's only going to take it, screw it, and come back, all the way down and come back, okay? So even though the last one, of course, the last one has to travel all the way through, right? It's traveling all the way through, but it's not gonna take this information. It's only gonna take that deep information, okay? Because we already have the other focuses focusing on that the shallow and intermediate depths, okay? So it's only gonna take, even though it travels the whole scan line, it's only taking the deeper information. Okay?
It has 2 focus, or
This is 3 focuses. 3 focuses. So however many focuses you have, that's how many times you're going to travel down that same scan line.
So for every particle, for example.
Particle.
Particle of the body. Every cell or every organ or.
Nothing to do with that. Nothing to do with that. Scan line is just sending 3 beams down the same scan line to create shallow, intermediate,
at the same
and
time?
deep. No, not at the same time, right? Just like I showed you, one after another. They can't send them at the same time, right? Because these are coming. How fast are these coming after each other, guys? 10 microseconds, right? 10 microseconds. So definitely not at the same time, but right after one another, almost the same time. Remember, the number's so minuscule you can't even tell the difference. Okay. All right. So I'm going to blaze through this, guys. We already talked about that. Just know, dynamic receive focusing, guys, it is performed automatically, okay? We don't control that as sonographers, okay? What that does is it improves lateral resolution as doing reception, okay? Everything I bolded on here. Guys, I'll send you what I have so far today, because I have everything concerning the transducer today. I have to finish the special topics, and boom. It'll be done. So by Friday, you have every single thing I have. Test on Monday. All right? So let's do our linear phased array recap, guys. Before we even get into that, let's talk about linear phased array. So how many crystals are in a linear phased array transducer, Myra? Anybody? Somebody help out.
100 to 300.
100 to 300. Guys, I'm not going to lie. You're just going to have to put those crystal numbers to memory. That's what it is. You're going to have to put those numbers to memory. Okay? The thing that makes a linear phased array unique is that even though the transducer face or the scan head is flat, it's still creating a sector image. That's what makes it different from a regular linear transducer, right? Mm-hmm. It's the image shape that it's creating, because of how it fans or does that windshield wiper blade bicycle spoke kind of image shape, how the beam radiates out of each scan line. Okay, how is it steered? That's one word. Electronically, right? Electronic steering, right? How's the focusing? Electronic focusing, guys. Electronic focusing. What kind of image shape again?
Fan, sector.
Sector image shape. What happens when there's damage to the PZT of a linear phased array transducer?
Inconsistent.
Inconsistent. It can't be determined what's going to happen to that image. Okay. I think I even added on there. Forget that, we're not going that far back. Okay, so let's do our little recap of linear phased array. So, again, another thing is all the crystals in a linear phased array are used to create that one sound beam, right? So all the crystals are going to be activated 10 microseconds after the other one, correct? All right. So multiple electrical signals are used to create a single acoustic pulse. Okay. What's that principle that makes this beam hourglass shape? Constructive and destructive interference. Huygens principle, Huygens principle, however you want to say it. Just recognize it when you see it. Okay. All the crystals are fired nearly simultaneously. Again, how many seconds apart is that? 10 microseconds. 10 microseconds. Each crystal produces its own small sound wave. That means each crystal has its own what, guys?
Its own wire.
Its own wire, its own channel, its own wire. It's connected to the sound system by itself. Okay? These multiple waves interfere, constructive and destructive interference, creating a single pulse that is focused and steered. Okay? What happens? What steers the beam? Somebody, one person tell me what makes electronic steering? The slope. The slope. Remember those two S's, guys. Steering, slope. Remember, if it has a slope, what is actually being sloped though? I can't hear you, Pat. The electronic signal. The spikes, the electric spikes being sent to the actual PZT is what's actually being sloped. That's what's gonna steer the beam one way, or steer the beam the other way. Or if it's in a straight line going straight across, it's going straight down, correct? Okay. So, and again, for focusing, that means just like I always think about focusing is always going to be about curvature, right? Mm-hmm. Think about our internal focusing, which is done with a curved PZT element, right? Think about our external focus, which is done with a curved what? A curved lens, acoustic lens. And also having curved excitation patterns is going to create our focus, narrow our beam, okay? Remember, guys, if our excitation pattern is far away from the transducer, or far away from the elements, shallow. That means we're going to have a shallow focus. Okay, the further away from the elements, the shallower the focus. If the elements are excited near the elements, there's going to be a deeper focus. Okay, we have control over that, right? Because we adjust that all the time. Whenever we change our focal depth, whenever we change our focus, that's what we're changing. We're actually changing the excitation pattern, the curvature of those excitations. Okay. Okay, so some advantage of linear phased array, guys, it's electronic, no moving parts. It's not like a mechanical transducer or an annular array transducer, right? Okay. It is also sonographer controlled. The transmit focusing is. Remember, we don't control what, guys? The dynamic receive focusing. We control the transmit focusing, but we don't control the dynamic receive focusing or just dynamic focusing. Okay, so you might see that both ways. Okay, that's already established upon reception. Remember, dynamic receive is upon reception. That's already established by the ultrasound system itself. Okay, and it has a small acoustic footprint. Right? This is when I said right here that I said James likes to use it, right? Like when I think I was in lab. I was in lab with a group of students, and I was talking about how big the 12 is versus having a little sector. You're able to squeeze in a little spaces a lot better. Okay.
Is that what they use for the? We use it yesterday for the vascular, right?
Probably not. Probably not.
It's
You
the one that
can
has
use
the
it for
red on the top, right? The skinny red. It has a red.
It's a little
instead of
square?
red. Yes.
It's a little square? Yeah, that's it.
Yeah.
That's it.
Yesterday.
Really? For vascular? James?
No, not James. My specialist was using it yesterday. She had a patient.
Okay.
Yeah.
Nazar using that? Because that's only thing I don't like about this transducer is a real grainy image. It's not a real pretty image. It's super grainy. It doesn't look great to me at all. Okay? Some disadvantages is it's expensive and it's complex, right? And the fact that if something happens to the trans elements, then we can't predict what's going to happen. Our transducer may be good enough, it may be still good enough to use, But then sometimes it may be bad enough that we got to take it out of service. We may have to get a new transducer. We can't predict it. Okay? Potential for grading lobe artifacts, image quality by degrading lateral resolution and creating artifacts. Grading lobe artifacts, guys, meaning that it has, the beam has a certain shape, right? Grading lobe artifacts are outside the beam artifacts. So the beam has low quality. So this is our beam right here. That's our beam right here. And so it has low quality beams still contributing to our image. So these are called grading and side lobes. And we'll talk about those and we'll talk about special topics at the end of this chapter. Okay? It's at the end. No worries. I'm going to cover it. All right? So, also, all the active elements are fired to create the sound pulse. All right. We talked about that already. So, that's our linear phase array transducer, guys. Remember how those active elements are being fired, specifically to the linear phase array. All of the elements in the linear phase array create the sound beam. Okay? All of the active elements. So, now, guys, we have the annular phased array transducer. Annular means circular, right? Round. Okay? This is a picture right here of an annular phased array transducer. I've never used one, guys. I can't say how that operates. Okay? But an annular phased array appears like a disc-like or circular disc-like transducer. Okay? Each one of these colors, yellow, red, green, purple, acts as an active element. They're all different active elements. They all have their own channel. Okay? Rather than a single element, the disc actually comprised of multiple ring-shaped elements with a common center. What would be we talked about this a little bit. What would be the purpose of this transducer right here? What would be the purpose of having multiple ring-shaped elements?
Multiple focuses.
Yeah.
Bang, there we go. Able to have different focal depths, right? Remember, transducer diameter is related to focal depth. It's directly related to focal depth, right? So this transducer right here is going to be able to focus our beam at many different depths. So this depth right here is going to be for shallow, right? Because it's the smallest diameter in a direct relationship. So small diameter crystal, shallow depth, right? And as it goes out, it's going to go deeper. Okay, so this transducer is able to have multiple focuses at different depths. Okay, this appearance is similar to the rings that appear on the bullseye target. Remember that, how you remember annular phased array transducer. Kind of looks like a bullseye target. Okay, creates a fan or sector-shaped image, guys. Everything we talked about, guys, have created fan or sector-shaped images, right? Mm-hmm. Whether it be the mechanical transducer, the linear phased array transducer, or this one right here, the annular phased array transducer. Okay? The first three transducers we talked about all create sector-shaped images. All right? Okay. So that means sound beams are emitted from the transducer like spokes of a bicycle wheel, like a windshield wiper, right? Had that appearance just like this. All right? So that's what it looks like right here, guys. This is what the elements of a annular phased array transducer look like right there. Okay. Multiple ring shape. They're not multicolored like the picture suggests, right? Just different shapes, all sharing a common center. Okay. Mechanical steering, guys. This transducer is steered mechanically. It's actually a motor spinning this transducer around. Okay, moving this transducer. Okay. A motor physically moves the ring element array so that the beams are transmitted in different directions. Remember, we're talking about steering. This is steering, right? Creating that sector-shaped beam. This is steering right here. Okay? So that's what's happening. So this actual transducer is being steered mechanically by a motor while it's in. What else is steered mechanically, Miss Cecile?
The mechanical.
Bang! There we go. That mechanical transducer is also steered mechanical. Those are the only two transducers, guys, that have anything mechanical. Okay.
This work the same as the mechanical as there is
It's
something.
It doesn't spin all the way around like that because that's a single element. It's probably just making that sweeping motion. That sweeping motion inside of the round head of this transducer. It's probably just making that sweeping motion like this. All rings. Yes, ma'am.
So mechanical doesn't mean that it has a motor, just the other
Absolutely. When we're talking about transducers, yes. Meaning it's something that's actually physically moving it. Mechanical means that something is actually physically moving it. Okay?
How many crystals does it have?
It varies. It varies. It does vary. It can have, I've heard them with the 4 crystals, 4 to 6 crystals, I would say. 4 to 6 crystals, I would say. Okay. Electronic steering, guys, is not possible with this transducer. Okay. Same thing. Electronic steering is not possible with a mechanical transducer. Okay. Angular phased array. The only 2 transducers that have mechanical steering. All the other transducers we talk about are going to have electronic steering. Okay. But it's an array transducer. Why, Farnaz? Why is it an array transducer? Why is this angular phased array an array transducer? No, it has multiple elements. It has multiple elements. Wasn't a trick question. Wasn't a trick question. Okay. So that's steering, guys. Major thing, mechanical steering. Anything in bold, that's what I really want you guys to know. Okay. Focusing, though. Electronic focusing. Electronic focusing. Okay. The primary advantage of angular phased arrays is that multiple transmit focal zones create each scan line of the image, like we said earlier. Okay. It has multiple transmit focal zones. Okay. According to the diameter of that PZT. We already know this, though, right? We learned about this talking about sound beams. Focal depth and divergence.
Here